All right, guys, today we're going to look at multiplying special cases of binomials. So our essential question for today is, what do you look for to determine if you can use a special pattern to multiply? So I want you guys to be able to kind of look at the binomials you're given to multiply and kind of analyze them to determine whether or not you can use a special pattern and which special pattern you would be able to use. Now, before we get to that, I kind of want to look at a few examples, and I want to multiply these out like we've been doing with double distributing. So looking at x plus 8 squared, the thing that's important to remember about when you're squaring a term is that you're multiplying it by itself. So last week we talked a little bit about repeated multiplication, correct? And we looked in our warm-up at x times x times x. And we said that that was the same thing as x to the third power. So if you have x to the third power, remember that expands to x times x times x. So in this case, if we have x plus 8 squared, that's the same thing as x plus 8 times itself. So x plus 8 times x plus 8. So we have two binomials, just like we saw in lesson 1.5, that we need to multiply together. So we're going to break apart our first binomial and expand it to the second. So we have x times x plus 8 plus 8 times x plus 8. And when we double distribute, we get x squared plus 8x plus 8x, and then 8 times 8 gives us 64. So when we simplify this, that's going to give us x squared plus 16x plus 64. So over here, same concept. If we expand this, this would be x minus 3 times x minus 3. And then if we break up the first binomial to distribute to the second, that's going to be x times x minus 3 minus 3 times x minus 3. Then I distribute, and I get x squared minus 3x. Negative 3 times x is negative 3x as well. And negative 3 times negative 3 gives us a positive 9. So watch those double negatives. And if we simplify, we get x squared. Negative 3 minus 3 is negative 6x plus 9. And then for this last one, I'm going to break apart this first binomial here and distribute it to the second. So that's x times x plus 7 minus 7 times x plus 7. When I distribute, I get x squared plus 7x. When I distribute this, I get minus 7x. And then negative 7 times a positive 7 gives us a negative 49. So we get here x squared, and then positive 7 minus 7. Those are going to cancel out, because if I have 7x's and I take 7x's away, I'm left with 0. And then I have minus 49. So I want us to look at the first two to start with, and I want us to look at the similarities here. So first off, notice that in both cases, we had a binomial to the second power, so a binomial squared. And if you look at what we kind of got as we went through our work, notice here we got two 8x's. Okay, so here we have an x and an 8, and when we multiplied it out, we got two 8x's. Over here, we got two negative 3x's. In our original binomial, we had x and a negative 3, and we ended up with two negative 3x's. This one right here has an addition symbol in the middle. If I look back at the binomial, I had addition symbol in my binomial. This one over here has a subtraction symbol in the middle. And if I look back at my original binomial, I had a subtraction symbol in the binomial. In both cases, we ended up with a positive constant. So let's kind of look into this a little bit further. What is the relationship between the original binomial and what we got at the very end? Well, right here, we have the first term in the binomial, x to the second power. And right here, we have the last term in the binomial, positive 8 to the second power. Well, did that happen over here? Let's look. X to the second power gave us our first term. And then negative 3 to the second power gave us our last term. Because remember, when you raise a number to the second power, you're multiplying it by itself. So negative 3 times negative 3 gives us a positive 9. So that held true here as well. Well, and then going back to what I said right here, that middle term is 2 of the product of what you have inside of the parentheses. So 2 times x times 8 gave us 16x. Did that happen here? Well, let's look. 2 times x times negative 3 gives us negative 6x. 2 times x times negative 3 is negative 6x. So there's this special pattern happening here that happens anytime you multiply two binomials. When you take a binomial and raise it to the second power, I should say. So when you multiply a binomial times itself, this special pattern is going to occur in every instance. So we're going to look at this on the next slide in general terms, where we can apply the same pattern anytime we're squaring a binomial. So that's the first two. This is what we call a binomial squared. And when we have a binomial squared, it ends up giving us what we call a perfect square trinomial. A perfect square trinomial. Because what happens is this term will be a perfect square, and this term here will be a perfect square. Same thing here. X squared is a perfect square. Oh, my marker's not working. This term right here is a perfect square, and this term right here is a perfect square. So these are our perfect square trinomials down here. So then we have something a little bit different over here. So notice that in our original multiplication problem, we had an x minus 7 and an x plus 7. So I'm going to call this 1 plus 1 minus. And when we have 1 plus 1 minus, something a little bit different happens. So we still have the square of the first term in our answer, so x squared, and the square of the last term in our answer, which is 49, but notice that it's now subtraction. Okay, so we are essentially squaring that second term, but it's always going to give us subtraction down here because when we expand it, we have 1 plus 1 minus. And if you have 1 plus 1 minus, that's always going to multiply out to be a negative value. So that middle term, every time, is going to give us a positive value of it and a negative value of it. So every time that middle term is going to end up canceling out because you're always going to take away the same number that you have, leaving you with 0. And this right here, this is what we call the difference of squares. So difference means subtraction. The difference of squares, x squared is a perfect square, and 49 is a perfect square. So this is our difference of squares pattern. So let's take a look on the next slide and look at these in general terms. So our first vocabulary term is the 1 plus 1 minus. And again, the 1 plus 1 minus gives us the difference of squares when we multiply it out. So I'm going to use the variables f and g as just kind of my general variables for any of the binomials that we look at. So if we have f plus g times f minus g, 1 plus 1 minus, that's always going to multiply out to f squared, which is your first term, minus g squared, which is the second term. Now, this is only the case when your terms are the exact same numbers. So these numbers have to be the same, and these numbers have to be the same. So the next one, and for this one, just keep in mind that this is called the difference of squares because it's always subtraction. So when you multiply it out, you're always going to get subtraction between the f squared and the g squared. Always subtraction. That's why it's called the difference of squares. So keep that in mind. And then the other one is when you have a binomial squared. And when you multiply out a binomial squared, that's always going to give us a perfect square trinomial. So in general terms, f plus g squared. We're going to expand that out using the special pattern. So we take the first term, we square it, plus 2 times the first term times the second term, so 2 times f times g, plus the second term squared, so plus g squared. And whenever g is negative or g is being subtracted, you're going to use the negative when you plug it into your special pattern. So we're going to work through some multiplying of binomials today using these two special patterns. And you guys need to make sure that in your assignment, in your practice problems today, that you are in fact using these special patterns.